Okay, so I started writing this out and to try to get a little ahead and make this go a little faster. But this is problem 79. It says in a titration experiment based on the equation above, 25 milliliters of acidified iron 2 solution requires 14 milliliters of a standard. That means you know what this is. Standard solutions with 0 molar permanganate solution to reach the equivalence point. It reaches the equivalence point, moles of whatever you mix together equals moles of the other thing. So moles of one equals moles of the other. So in this case, the moles of iron, the iron 2 ion, permanganate ion will be the same. So never ever forget, as soon as you see this is just PV equals nRT, as soon as you're given a volume and a molarity, you know how to get moles. Volume times the molarity is moles. So let's go up here. Don't look at this yet. Come look up here. So I rewrote the equation. 5 moles of iron 2 ion react with 1 mole of permanganate and 1 mole of hydrogen ion in this equilibrium. That means it goes back and forth. It's reversible. To produce 5 moles of iron 3 ion, 2 moles of iron manganese 2 plus ion, and 4 moles of water. These are the only two I'm concerned about because they didn't ask me about anything else. So I've got to figure out what the concentration was. I need moles per liter for this thing in the beginning. That is my question. I need moles per liter. Okay, so we didn't give us a whole liter, they just gave us part of one. So I wrote the information that they gave us above the substance. So 0.025 liters, 25 milliliters, of this iron 2 solution. That's how much we had. In that amount of solution, you're going to have X number of moles of the whole substance. So, because it came off of a compound. You know, you don't find Fe2 plus in a jar. It's got to come in some solid that you then dissolve in water, and then these ions separate. So this was a part of some compound X, okay? But that X part's just floating around. Remember, in that ionic equations, well, if it's going to be shown on both sides, we cancel it out, and that's what happened to this. So you could think about this as being iron nitrate, okay? Well, you're looking for the molarity of the solution you first put in there. But the balance, the ratio here is 5 of these to 1 of these, all right? So, back the same way we've been doing it over and over, and this is the information they gave us about the permanganate. We know that we are going to take our volume and our molarity and get ourselves to mole count. So, if you'll always just start with your volume, it just makes it easier. You just write your volume over 1, and then multiply it times your other. You could go the other way, it's not wrong, but you'll be set on a better path. You just write it over 1, okay? So, then you could skip this part. I was making notes to self. So start with your volume times the molarity of what you're given. So then these volumes are going to cancel out, and you have to then, so now you're in mole town, and you're going to do your mole to mole ratio, mole to mole ratio. For every 1 mole of this, you used 5 moles of the iron ion, okay? Now, the problem is you get moles of ion, but you're not finished. I used this piece of information. I used this piece of information. I haven't used this piece of information because this amount of ion, these moles of ions, were floating in this much solution. So I have to say times that moles per liter, so that's this was in 0.25 liters. And just like I put a 1 over here under that, I could put a 1 over here because I'm looking for moles per liter. We can see these liters canceled out, moles of permanganate cancel out. I'm left with moles of iron, and this is in the liters of the iron solution, okay? So that's how fast you can set that up and work it. Now, for the math, yes, you do not have a calculator, and yes, you are fully expected to work this. However, if you'll just do a little head play here. So 0.05 times 5. That's like, just say 5 times 5, and you get 25, but this was in 2 decimal places, so I'm going to move this understood decimal in 2 decimal places, and I've got myself from this 0.25. I've got to multiply that by the 0.14. I don't really like 4s, so you could round this to a 5, but no, you're estimating, okay? But at any rate, so you've got 0.25, and then you have to multiply it times the 0.014, and so that's 20, and then you get, what is this, 100, and so then 5 and 2, oh, look, I cannot add, I cannot write. So I should come up with, I should have come up with 280. Where am I? I need my 2. So then 0 and 5 and 2. Oh, 35. Okay, so I've got 35, 350. So now, but I need to come in how many decimal places? 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Okay, then I take that, and I'm going to divide that by the 0.025. And when I do, so I've resolved my numerator, and what I have looks like this. So 0.0035, 0 and 0.025 liters, these are moles, Fe, this is how many liters of my solution, and then, so you just go to it. So you go off to the side and you do the long division. Now, one of the cheat ways to do this is take these things out of the decimals, you just have to remember to put it back in. So if I come over here and I say 0.00350 divided by 0.025, if I just say 1, 2, 3 and 1, 2, 3, shouldn't I come up with the same proportion and take 25 into 3.5? So I've moved the decimal here, I moved the decimal here, so that's a valid maneuver. And when I do the math, that's not that hard. And so you expect easy math. You expect to do some math, but you don't expect it to be incredibly hard. So I have 0, and then so 25 goes into 35 one time, and then I take that off, and I come up with 10, and then 100, and 25 goes into there. So see how nice and easy that was? So I have resolved this to be 0.14 moles per liter, and that is the answer, okay? So that's one way to do it. So once you get it better, you'll be faster. Okay, now, back up. I'm going to show you 3 ways to do this, and you get to pick your way. But what you have to do is be fast and accurate, all right? Whatever, you have to be accurate, but you have to be fast. So if you wanted to use the other way, the M1V1, then you have to remember about your ends. But what I want you to do is think about this. You're going to get the molarity of the solution from which the iron came from. That's what this molarity is going to be. But for every mole of that substance, you got 5 irons out of it. So you're going to have to take that molarity, the moles you get, the molarity is going to solve for the molarity, and you're going to have to multiply that times 5. Where did that 5 come from? Over here. You have to remember to do that part. So I substituted in, this 1 is the one for that. So we can erase it. We don't have to put that there. Okay, so I took the molarity times the volume that I was given from up here. I multiplied those, and I got M times the, this is the molarity of the iron solution. This is the volume of that solution. Have to remember I have to multiply it times 5, so I wrote that over here. When I multiply these two things together, I come up with this number, 0.0007 moles. That's going to be equal to whatever that molarity is times this many liters. So now I'm still looking for this molarity, so if I take these liters and divide it by these moles, I'm going to get the molarity of this as being that Fe2 plus solution. So I did that down here, and I need you to think and the same thing. I need to move this over 3 places. I need to move this over 3 places. So now I've got 25 going into 0.7, which we can say here it's going to go in 2 times. So that's going to give us 50. But I think we have a 0 here. I need a 0 there. I messed that up somehow. 0.7. Yeah. Hang on. Yeah, delete. So this is a 0, and then you bring another 0, and you cut. It goes 25. That's 2. That's 50, and then I've got 20. And see how smooth this goes in there? That's 8. All right. So this I come up with 0.28 moles of the FeX, whatever it was in, nitrate or whatever. That's the molarity of that solution. Okay. So now, how do I know that? Because moles of this was equal to moles of that. Got those moles and plopped it in however much solution they gave me. But now for every mole of this, I have 5 moles of that iron. So I just have to remember, I have to come back and multiply it by that 5. And when I do, I come up with, again, that number. All right? So I'm going to erase this. I'm going to pause, erase this, come back and show you the table method way. Okay, so table method. We have, so what we're going to do is take what we're given, and we're going to write our mole ratio. Okay. So our mole ratio, or you can do moles first, either way. So this is 5, and this is 1. And how many moles of this do I have? Well, I know that M times V is moles, and the 0.05 moles per liter times the 0.014 liters, that's going to give me that 0.0007 moles. So now I know 0.0007 moles. That's the 1. 5 times as many moles are going to go from the iron. So when I multiply that times 5, I'm going to get that 0.035 moles of that. Now, the only thing you got left to do now is take these moles and put them into this to figure out your mole per liter ratio. So if I had more room down here, I'm going to write in red. Maybe you can see it through the writing. So 0.025 liters contains this many moles. My question is, what is the concentration? So I have to get it mole per single 1 liter. So again, I just do that math, and I come up with the 0.14 moles per liter. Okay, so by far, in my mind, the very quickest way is the table way. But you get a choice. What you have to remember, though, is that your moles are floating in solution. That's your biggest thing with these, is to remember that. Okay, also, if you're doing these problems and you're adding 2 solutions together, their volumes are additive. Okay, now, they didn't ask us what the final concentration was. They asked us the original. In the original, this was our original volume. If they had asked us for the concentration after, then that would be additive. We would have had to have added the 25 and the 14. That wasn't the question. Okay? All right. So I hope that's clear, and I'm going to do one more. Okay, 1994, number 16. Commercial vinegar is titrated. Titration. Base. I got an acid base. I got a M molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base, as long as I keep my mole ratio in my mind. So, to determine the content of acetic acid, so for 20 milliliters, so we're titrating acetic acid and sodium hydroxide. For 20 milliliters of vinegar, 32 milliliters of a 0.5 molar solution were required. What does that mean? It means it took this many milliliters of this molar solution together, that gives you moles. That many moles of NaOH were required to neutralize 20 milliliters of this vinegar. Okay, so you have 20 milliliters of the vinegar. So you can write that as HAC actually. Acetic acids, we'll just go with this. All right, so now, I am going to need to know what this relationship is. So by this point, if you look at this, you have one hydroxide and one hydrogen. You have one sodium and this. So you know this has to be a +1 because there's only one hydrogen hooked on here. So this has to be a -1, and this has to be a +1. So since this is a 1-to-1, this is going to be a 1-to-1 relationship. This is 1, this is 1. So this is easy greasy now, because I do not have to worry about any multiplying after that. So what they give me? What are my moles of acid? What am I looking for? To determine the content, what was the concentration of the acetic acid if no other acid was present? So I'm looking for concentration. So this is my question. That's my question. So let's fill in. We've got the molarity of the acid then, and this is going to be, I can rearrange this, right? Thank you. So molarity of the base times the volume of the base divided by the volume of the acid. And that's going to be, what do we have? 0.5 moles per liter of the NaOH. And we have how many? 32 milliliters changed to liters is 0.032 liters. And that then divided by, see how my liters cancel out? And I'm left with moles. I'm going to divide that by the milliliters of the acid, which was 20. So 20 milliliters is 0.02 liters. So if I take, okay, now I am nitty-gritty looking for time. Half of something of a 32, right, is going to give me a 16 something, yes? So some form of 16 divided by this is going to be some decimal to so many places back, divided by something 2 is going to give me something 8. Go look for something that's a point something something 8. Do we have one? No, 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 no. Yes, right there. And there you go. Because this is moles per liter. This is moles. This is liters. You're going to come up with that. So did I have to go do all this part? No, I didn't. Because they are going to give me answers that are far enough away from each other that I can use some estimation. Now, did I... See, look, but there's always the trap. You see this one? That one right there is in case you decided not to go ahead and divide it by the volume. So you just got the moles of the sodium hydroxide. So that's how I worked it. And that's how you do it. That's how you just estimate and roll. Because, I mean, do you see what I did? Like some part of the, I mean, you can go over here and work it if you want to, but some half, 0.5 is half, some half of this 0.032 is going to be what, 0.016? Divided by 0.02 is going to give you 0.8. So you have 0.8 moles per liter, all right? So that's that one. Okay, so this question says, if 87 grams of potassium sulfate with a molar mass of 174 grams is dissolved in enough water to make 250 milliliters of solution, oh good, we're making a solution. What are the concentrations of the potassium and sulfate ions? What are the concentrations of the potassium and the sulfate ions? Well, guess what? I've got K2SO4. When this ionizes, I get 2 K plus and 1 SO4, 2 minus. All right? So we're putting it in water, and so when we do this, so this is solid grams, okay? And they're adding it to water, so in water, and that's what you're going to get. All right? Now, so I do not want to look at any 87 grams and 174. I'm rounding. So I'm taking this to 90, and I'm taking this to 180. And do you see a relationship? So let's just say I've got 90 grams of K2SO4, and its molar mass is close to 180 grams per mole. Don't I have about a half a mole? Yes, I do. 90 divided by 90 goes into 180. Okay, so now that's about how many moles of this I have, and this is of the K2SO4. For every one of these moles, 0.5 moles, for every one of these, I'm going to get, and you don't have to write this out, you can ballpark it at this point. So I've got, look, 0.5 moles. If this is 1, then what is 2? 1. If this is 1 and this is 1, what is this? A 0.5. Well, you know they've got to go in at, we're making 250 milliliters. They've got to go in at this 2-to-1 ratio. But they're going in 250 milliliters of solution. So if I take the 0.015 moles and I put it in 250 milliliters of solution, so 250 milliliters is 1, 2, this is 0.2, all right? So what am I going to get? What's that relationship? And then take the same thing over here, and not that one, but this one. And then, so this is 1 mole in the 0.250. So I can look and see that this one is going to be 2 molar, and this one is going to have to be 1 molar. Well, even before I did any of that, I can eliminate. I can just go by the process of elimination. I didn't really have to do all that part. I know I'm getting 2 to 1. 2 of these to 1 of those. So this is wrong because they're not equal molar. That one's out. I'm getting twice as much here as this. That one's out. 2 to 1, that may work. 2 to 2, that does not work. 2 to 4, that may work. So now, then, this is why I have to know which one is which. So I come up with, if this is not 2, that's 4. What am I doing? So if this is 2 molar, then this is, because this is a quarter in that, yes, so 4 molar. So then this is your answer. So I only had to go here to figure this part out because I had another answer that would have worked. But you always want to skim this kind, Because if they didn't have another 2 to 1, sometimes they won't do that. They'll have like, this will be a 3. And you can just go by process of elimination. So, but the first thing you had to do with this was look at it and say, they're just making a solution. This is going to fall apart. I'm going to get 2 of these to 1 of these. So whatever your molar ratio is, it's got to be 2 of these to 1 of those. So there's that one. Number 55, what volume of a 1.5 molar HCl solution is required to neutralize barium hydroxide? Oh, check, check. Look here. Here's your trap right there, that 2. You got to know, you got to think about it. Every time you see a neutralization, you got to think how many hydroxides are on there, how many hydrogens are on there, because you have to write your balanced equation to make sure that you know what you're doing, unless you've just done it enough that you're cool with it. So, because when I try to write this, barium is a +2, this is a -1, I'm going to have Ba, I'm going to have 2 of these, right? 2. That means I've got to have 2 waters. So, I am looking at a 2 to 1 ratio, all right? So, 2 to 1. Now, M1, so this is a neutralization, and I can do this is equal to molarity of the base times the volume of the base, but I have to remember this is 2 times that molarity, 2 times the molarity of that acid. So what do I know? I have a 1.5, I have 0.1.5 molar solution, and I am asked for the volume of that solution. And see, they can ask me any one of these. And then I have a 0.120 moles per liter of the barium hydroxide. And I've got how many? 0.0250 liters. And then, so this is moles per liter. I didn't put my unit. So 2 times that, that's what I'm going to need. So 2 of the 0.105 moles per liter. Alright, so what volume? So what does this resolve itself to be? Well, looking, I've got what is 0.025 times the 0.12. Well, that's a quarter of 12. So that's going to be, or 0.12, so that's going to be 0.003 moles. My liters canceled. And those moles, this is going to be, I'm going to divide that by the 100 and the 0.15 moles per liter to isolate this volume. This is my volume, is my question. So I'm going to divide that by the 0.15, and so then I should come up with something along the lines of a 2. So that is going to be 0.02. This is moles per liter, right? Moles per liter. And then, so this is going to be liters, right? And that's a good thing, because that's a question it asks us. There's one on the top. This is the liters, so it gets brought forward. So how do I know that? Because I'm just saying this is 30, this is 15, and 15 goes into 30 2 times. But I've got to back it out by all these decimal places. So Now, that's how many liters would make it even Steven. But I need 2 of those, remember? So I've got to say times 2. And that's going to give me 0.04 liters. And that is, in fact, 40 milliliters. And there we have it. Okay? So, expect easy math. That's the biggest picture here. This is more common, where you get this 0.12. They're always going to be decimals, guys, so get over it. Learn how to remove the decimals mentally and look at it. And think about it as being 12 times 0.25. You know 0.25 is a quarter. How did I do that? Well, I just erased that, and since I moved that one, then I moved that one. That's about a quarter. So you're at about 3 something. All right? So even if you just estimated and you said 3 something divided by the 0.15, that's going to give you a 2 something, and then this 2 something times the 2 over here is going to give me a 4 something milliliters. So there's only 1 4 there, and that's the 40 milliliters. Okay? Next. Okay, so number 56, 2 more. Number 56. It is suggested that SO2 with a molar mass of 64 grams, which contributes to acid rain, can be removed from a stream of waste gases by bubbling the gases through 0.25 molar KOH, thereby producing K2SO3. What is the maximum mass of SO2 that could be removed with 1,000 liters of KOH solution? Okay, I'm whipping through these, and I did not mention to you something. Okay, you see the period where that decimal right there means that there are 4 significant digits here. Sometimes on these problems, guys, you just, listen, I hate to throw this at you, but if you see 2 answers that are alike and the only difference is the number of significant digits in which they are presented, heads up, alert yourself, okay? So just pay attention to that. That's not the case here because none of these even look the same, but, you know, you do want to pay attention to that. So, we have this reaction where we're going to have SO2 plus KOH, and we're going to be making K2SO4. What else is made here? You don't know, right? Okay, well, heads up. Here's how it works. You see this OH. Obviously, an oxygen must leave the hydroxide and go over here. So that's what happens, all right? That's one of them. So this becomes SO3, all right? The other one, this H plus, is going to hook up with another of those. This KOH will split like this. So this splits to here, and then this one's going to split. Go that way. Doesn't happen often, but it does happen in these reactions. So then these make a water, all right? So anytime you've got these hydroxides around and they're going to mix up with some SOx, you heard me say that today, SOx. Well, you can have SO3, SO2, SO4, whatever. So we call them SOx. You can also get the same variety in the nitrous oxide or all those. So we call these the NOx. And don't laugh, but we also can do CO2 and CO3 and CO, and so we call those the COX. So SOx, NOx, and COX, all those things go together. When they react with something like a strong acid or a strong base, they rearrange and produce these salts, and they also produce water. So now all we have to know is we need to know their molar ratio, I guess. And what is that? So 2 of these. And we knew that because we have 2 of those, right? So, and that would make it balanced. So, I have a 0.25 molar solution, and that's moles per liter, and they said 1,000 liters times 1,000 liters. So that's going to give me how many moles? I need to move my decimal place 3 times. So that is 250 moles. Well, guess what? Of what? KOH. So if 2 is equal to 250 moles, isn't 1 then, because this is a 1, that ratio, this is going to be 125 moles, right? So 125 moles times the 64 grams per mole they gave us, we should come up with 2, and that's carry 1, that's 5, and 0, and 0, and carrier 3, and you should come up with, so, what did I do? So, okay, so starting over. 0 and 3, and so that's 30, carrier 3, and you get a 5 for 15, and then a 7. So then you add them up, and you have 8,000 what? Grams, right? Because wasn't this moles, and then this was grams per mole? And if it makes better, you can make it very formal and say 125 moles is what I have. How many grams is that? Because it asked me for mass. And so 1 mole has the 64 grams. See, on these, nobody's reading your work. You're just scratching on the paper. You're just looking for multiple choice answer. So, but you need to be neat and organized as you do it so you don't make mistakes. Anyway, that becomes 8,000 grams, which in fact is indeed B, 8 grams. Isn't it getting easier? Just say yes. Okay, last one. A 1 liter sample of aqueous solution, a 1 liter, there's a volume. I need to pay attention to these. Get out of here, stop that. Go back. What you doing? What's that? That's a problem we already did. Okay. I'm not knowing. I guess it copied itself. I don't know. Here, let's just do this. Okay. Oh, Lord, I don't have time for this. Come on. Yeah. Okay, I have 2 minutes to finish. Or less. But this one's really easy. Alright. A 1 liter sample. I'm writing up here. They're giving me a volume. I'm taking note. A 1 liter sample of an aqueous solution contains 0.1 moles of NaCl and 0.1 moles of calcium chloride. What is the minimum number of moles of silver nitrate that must be added to the solution in order to precipitate all of the calcium chloride out of solution? So you have a bunch of these that are reacting with the silver ion, and making this. Okay, so, in order to precipitate up thing. Alright, so I've got to figure out, they want to know the number of moles. They want to know moles of this that are going to be required to react with all of this. So that means I have to know total number of moles of this, right? Well, I've got a solution, and I have two sources of calcium ions. This is CaCl2, so for every one of those, I got that. So, I'm just going to add up all those moles I have. So, from the sodium chloride, 0.1 moles of sodium chloride, I am going to get, that's 0.1 moles, I'm going to get 1 mole of the chloride ion. And then, plus, from this 0.1 mole of the calcium chloride, I'm going to get 2 moles for every one of those. So that's going to be 2 times the 0.1 moles. And all of this is in a liter of solution, right? So that's going to give me 0.1 moles plus 0.2 moles to get the 0.3 moles. And so I have 0.3 moles of this calcium chloride, and that's in a liter. So how much is it going to take to react with that? Well, I'm going at a 1-to-1, aren't I? So my answer has to be, so this is a 1-to-1 to make this. 1-to-1. And so that's how many moles of this I have. That's how many moles of the silver nitrate I need. Walla bing, walla bang, we're done. See you mañana. There's a